You type in where you want to go, you tap Start, and in under a second, your phone hands you a route across a whole city, sometimes across a whole country. So here is a simple question. How did it choose that route? The obvious answer is, it checked all of them and picked the best one. But it didn't, it can't. And this is where it gets interesting. In a real city, the number of possible routes between 2 points isn't big. It's astronomically big. Checking every single one would take longer than your whole trip. It might take longer than your whole life. So navigation apps do something much smarter. Let me show you what's actually happening in that 1 second. First, the app has to turn the real world into something a computer can think about. So it strips the map down. It throws away the buildings, the parks, the street names. It keeps 2 things. Every place where roads meet, every intersection becomes a dot. We call each dot a node. A node is just a point the map cares about, usually an intersection. And every stretch of road connecting 2 dots becomes a line. We call each line an edge. An edge is a road segment, the connection from one node to the next. Dots and lines, nodes and edges, put them together and you get this. This is called a graph, not the kind with bars and axes from school, a different thing that happens to share the name. A graph is just a set of points connected by links. That's it. That's what a road map is to a navigation app, a graph. But we're missing one thing. Roads aren't all the same. Some are long, some are short, some are slow. So we write a number on every edge, how long it takes to drive it, say in seconds. That number is called the weight of the edge, its cost. A bigger weight means a slower road. Now the question, what's the fastest route, has a clean shape. Find the path from start to end where the weights add up to the smallest total. So how do you find that smallest total without checking every route? Here's a beautiful idea from 1959, from a computer scientist named Dijkstra. Imagine standing at your starting point and pouring water onto the map. The water spreads out along the roads. For now, let's keep it simple and imagine every road runs at the same speed, so a road's cost is just how long it takes to cross. The wave spreads outward, and at every moment it flows into the cheapest place it can reach next. The app does the same thing, but with numbers. It keeps a running total for each node, the fastest time it has found so far to reach that node. And at every step, it does one simple thing. It looks at the edge of the wave, all the places it could go next, and it always steps to the cheapest one first, the one with the smallest total time so far. We call that edge of the wave the frontier, the border between what we've explored and what we haven't. Cheapest first, always step, update the totals, step again. Watch what happens. The wave grows outward, and every time it reaches a node, it has reached it by the fastest possible way. Why? Because we always took the cheapest step available. There's no shortcut we skipped. If a faster way existed, the wave would have gotten there first. And the moment the wave touches your destination, we're done. We trace the path back, and that is the guaranteed fastest route. This method has a name, Dijkstra's algorithm. An algorithm is just a fixed set of steps that always gives the right answer. And notice, we never checked every route. We just kept taking the cheapest step, and the fastest path fell out on its own. But there's a catch. Did you see the problem? Dijkstra's wave spreads everywhere, forward, sideways, even backward, away from where you want to go. It's careful and it's correct, but it wastes a lot of effort exploring roads in the wrong direction. So can we give it a hint? Can we tell it roughly which way the destination is? Yes, and here's the elegant part. Even without knowing the roads, we always know one thing: the straight line distance to the destination, as the crow flies. That straight line distance is a guess at how much farther we have to go. And if we assume the fastest speed anything could possibly travel, we can turn that distance into a guess of the time still ahead. We call a guess like this a heuristic, an educated estimate that points the search in the right direction. Now we change the rule slightly. At each step, instead of just picking the cheapest node so far, we pick the one with the best combined score, time already spent, plus that estimated time still to go. That one change pulls the whole wave toward the destination. It explores far fewer roads and it gets there much faster. This version has a name too, A star. A star is just Dijkstra plus that hint. But in this matters, the hint has to be honest. The rule is, the guess is allowed to be too low, but it must never be too high. It can never claim the destination is farther than it really is. We call a guess that follows this rule admissible. And our guess is perfect for this. A real road can only ever be longer than the straight line between 2 points, never shorter, and you can never beat that top speed. So the estimated time is always a little too low, never too high. The guess stays safe, and A star still finds the true fastest route. Okay, until now we made one big simplification. We pretended every road moves at the same speed, but real roads are messier than that. Where does that time even come from? It's built from a few things. How long the road is, and how fast you're allowed to drive it. A highway and a narrow side street can be the same length, but take very different times. Length divided by speed gives you time. That's the weight. But there's a sneakier cost, and it's easy to forget: turns. Turning left across busy traffic takes time. So a left turn can carry its own extra cost, added on top of the roads. And sometimes a turn isn't slow, it's simply not allowed. This is a subtle point. The road is there. You can see it, but you're not permitted to turn onto it from this direction. We call that a turn restriction. The edges exist, but the connection between them is blocked. A good router has to respect that, or it'll tell you to do something illegal. So the graph is richer than it first looked. It's not just roads and times. It's roads, times, turn costs, and rules about which turns you're even allowed to make. Now for the part that changes everything: traffic. Up to now, we imagine the waits, the travel times sitting still. But roads don't behave. A clear road at 3 a.m. is a parking lot at 6 p.m. So modern navigation systems don't use fixed times. They update the weights of the edges live, using real traffic conditions. Where does that traffic data come from? Partly from other drivers, huge numbers of phones, moving along roads, quietly reporting how fast traffic is actually flowing. And once the weights can change, something surprising happens. The shortest route stops being the fastest route. Look, this route is shorter in distance, but it's jammed. And this route is longer, more kilometers, but it's moving. So the app sends you the long way. And it feels wrong. You can see on the map that it's telling you to drive farther, but it's counting time, not distance, and in time the long way wins. This is the whole reason the app replans as traffic shifts through the day. The map is the same, but the weights are alive. Now let's make it hard, really hard. A single city already has thousands of intersections. A whole country has tens of millions. Even a star, as clever as it is, would have to crawl across a huge slice of that map for a long trip. Do that for millions of people every second, and it's just too slow. So here's the key idea that makes continental navigation actually work. You don't wait until someone asks. You do the hard thinking ahead of time. Think about how you plan a long drive. You don't think street by street. You think, get to the highway, take the highway most of the way, get off near the destination. The highway part doesn't change from trip to trip, so why rediscover it every single time? The trick is to build shortcuts in advance. Ahead of time, the system studies the map and precomputes fast paths across whole regions, and stores them as single long edges. So instead of a highway made of 1,000 little segments, you get one shortcut edge that says, Region A to Region B, here's the time, already worked out. And you can stack these, shortcuts over shortcuts, small roads at the bottom, bigger roads above, long distance shortcuts at the top, layers. We call that a hierarchy levels, from local streets at the bottom to continent crossing shortcuts at the top. Now a long trip is easy. Climb up out of your local streets, ride the top level shortcuts most of the way, then drop back down into local streets near the destination. The search skips over enormous regions. It never has to look inside. A query that would have crawled the whole map now finishes in a blink. Different systems build these layers in different ways, with names like contraction hierarchies or customizable route planning. The details differ. The core idea is the same. Think ahead, build shortcuts, and let long trips skip the boring middle. This is the quiet engineering that turns impossible into instant. One last thing, real driving never goes to plan. You miss a turn. Notice the app doesn't panic, and it doesn't start over from your original starting point. It re-anchors to where you are right now. Then it grabs the current traffic weights and runs the search again from here to your destination. And in a blink, you have a new route. But that raises a question we skipped. How does the app even know which road you're on? Your phone's location isn't perfect. Satellites give it a position, but it wobbles a few meters here, a few meters there. Between tall buildings, it can jump around. So the app doesn't trust a single raw dot. It looks at the trail of recent points, compares it to the road network, and figures out the most likely road you're actually on. Then it snaps you to it. That step, turning noisy location guesses into "you are on this road," is called map matching. It's why the little arrow glides smoothly down the street instead of hopping through people's back gardens. And that's the whole trick. Turn the map into a graph. Give every road a weight. Let a wave find the cheapest path and aim it with a smart guess. Keep the weights alive with traffic. Precompute shortcuts so even a continent fits in a blink, and replan the moment reality changes. Not one giant search of every possible road. A handful of genuinely clever ideas working together in the second between you tapping start and the road ahead lighting up.